In this video, we're going over the concepts of Chapter 11, which is titled Introduction to Organic Chemistry. When we talk about organic chemistry, we must first establish what are organic compounds. Any organic compound is going to have carbon. Now, carbon is an element that is a nonmetal that may be found in bonding events with other atoms that include hydrogen, oxygen, sulfur, nitrogen, phosphorus, and or halogen. Because most of the elements or atoms that I just mentioned are nonmetals, as well as carbon, that means that many organic compounds in essence have covalent bonds. When it comes to the physical properties, specifically for organic compounds, it is important to note that they have low melting points and boiling points when we compare them to ionic compounds. Organic compounds are also flammable. As we're going to see at the end of the chapter, they can undergo combustion reactions. Many organic compounds have nonpolar covalent bonds. Thus, the majority of the molecules are insoluble in water because the molecule itself is nonpolar. If there's any occasion where there's an organic compound that is soluble in water, it will be presented as such in the presentation. Now, where do we find these organic compounds? As you can see in the list in the last bullet point, or in the image that we have on the right side of the slide, we can observe that organic compounds are everywhere. It can be found in the gasoline that you use to power your car, in the medicines that sometimes you have to intake when you have an illness, plastics, perfumes, papers. All of them constitute an organic compound. Now that we are talking about organic molecules, it is important that we know how they are illustrated. Thus far in the semester, we have seen how we can represent the elements in a compound by looking at their molecular, in other words, their chemical formula. Now, the chemical formula only gives you the elements present and the quantity of them that you have in a particular compound. But it gives you no insight into the structure until you look at an actual model for the molecule or you look at a Lewis molecule. So in essence, the Lewis structure for a molecule is the expanded structural formula. Because when we look closely at the molecule, we see the atoms connected together and the bonds are stretched out. In other words, they are expanded. In organic chemistry, we illustrate molecules in two different formats. The first one is the condensed structure, which a condensed structure, when we look at it in detail, is just taking the atoms that are connected to one another and just writing them next to each other. So for example, if we look at the molecule here from the Lewis structure and we compare it to the condensed structure, what we can observe is, and I'm going to use my highlighter in order for specifically look at the atoms. This carbon atom is connected to 1, 2, 3 hydrogens. That's why it's a CH3. Understand that if it's written as an H3C, it is the same thing. Because what basically it is illustrating is that this carbon atom is connected to 1, 2, 3 hydrogens. So in organic chemistry, if something is written as CH3 or H3C, is the same thing. As we move along the molecule, we can see a series of carbon atoms connected to 2 hydrogens. That's why they are illustrated as CH2s. So if I highlight those, we can see that this is a CH2. Next, there's a CH2. Next, there's a CH2. there is a CH2. And then at the end of the molecule, we can see another CH3. Carbon connected to 1, 2, 3 hydrogens. So that's why it's written as CH3. Another important illustration that is commonly used in organic chemistry is going to be a skeletal structure. And it comes to a skeletal structure, what we can observe is that this, as I zoom in, a skeletal structure, what is going to illustrate in essence is the electron group geometry for the different carbons that we have in a structure. So we can observe that, for example, in this particular organic compound, each one of the carbon atoms is tetrahedral because there are 4 electron groups around the carbon atom. The skeletal structure, it illustrates specifically the electron group geometry of the carbon atoms. In a skeletal structure, we do not illustrate carbon atoms or hydrogen atoms connected to carbon. What you see illustrated here is that this carbon atom is the start of the line structure. And then as we move up, what this is representing is the angle 109 between these 2 carbons. So this line represents these 2 carbons. And you can see as we trace it based on the electron group geometry, we go carbon 1, 2, 3, 4, 5, 6, which is what we see illustrated here. Carbon 1, 2, 3, 4, 5, 6. Another thing that it is important to note is that a skeletal structure, if it's hard for you to visualize in the beginning, can be turned into a condensed structure. And this is how we perform that. Since we know that the start of a skeletal structure has a carbon, it is important to actually also understand that at each vertex, there is a carbon atom. So we can see the 6 carbons in this molecule. Furthermore, we can observe that by placing the hydrogens in, and this is how you determine how many hydrogens are on each carbon atom. One of the things about carbon is that carbon is a molecule that has an octet. An octet means that it needs 8 electrons. In this organic compound, that is signified by single bonds. So for example, if I look specifically at this carbon, since it is connected to only one thing, in order to fill its octet, it needs 3 things attached. And since the molecule, as an example, only has carbons and hydrogens, then that's why that carbon atom needs 3 things. They are hydrogen atoms. So that's why that carbon atom, overall, we write it as a CH3. Next carbon atom is connected to 1, 2 bonds. In order to get an octet, it needs 1, 2 things attached to it. Since this molecule only has carbons and hydrogens, this is a CH2. As you can see, the rest of the carbons are CH2s except the end one, because since this carbon atom is only connected to one line, in order to fill its octet, we need 3 hydrogen atoms. And this is how you easily convert from skeletal to condensed. Make sure that you practice how to identify and write correctly both condensed and skeletal structures, because those are going to be the illustrations that we will mostly be using when it comes to organic chemistry. The next thing that we need to focus when it comes to organic compounds is that these molecules have a specific way in which atoms that connect to carbon are bonded to one another. In general, this is what we know in organic chemistry as functional groups. There are a large number of functional groups, but in this course, we're only going to be focusing on a subset of functional groups. Additionally, I decided to group these functional groups into three large families. So there may be a little bit of an easier time for students to identify what are the different types of bonding that we see of carbon atom doings in these instances. Let's start by looking at the family of compounds that are known as hydrocarbons. If a molecule is known as a hydrocarbon, then what that means is that you can only find carbon and hydrogen atoms in the molecule. There are four members for these functional groups. We have an alkane, which means that we have carbon atoms connected to each other by a single bond. We also have single bonds to hydrogens. Notice that many of these have the R. And an R in organic chemistry means rest of molecule. The rest of molecules simply means that you will find either hydrogens or carbon chains extending from that signature connectivity that we have for a particular functional group. So as I mentioned, for an alkane, we have carbon-carbon single bonds and carbon-hydrogen single bonds. For an alkene, what we have is at least one carbon-carbon double bond. And then you have the R groups, which can be hydrogen or they can be carbon chains. Next, we have an alkyne. In an alkyne, we have at least one or more carbon-carbon triple bonds. And then the R groups can be hydrogen or carbon chains. Lastly, we have arenes. And arenes are actually illustrated by having a hexagon with alternating double bond, single bond, double bond, single bond, double bond, single bond. And they have to alternate like that. That specific structure of having that hexagon with the alternating double bonds and single bonds is known as a benzene ring. But the functional group is known as an arene. Let's next explore the family of functional groups that are known as heteroatomics. The reason why this family is known as heteroatomics is because we have atoms other than carbon in these structures. In the first functional group, which is called an alcohol, this R group is going to represent a carbon chain that has an OH group attached to it. In the functional group called an ether, we have an oxygen atom connected to two carbon chains, one on each side. The next functional group that we have is called a haloalkane. Haloalkanes are also known as alkyl halides. And for these haloalkanes or alkyl halide molecules, what we have is that we have a carbon chain connected to X. X specifically is going to be any element that is in group 7A of the periodic table, meaning the halogens. Next, we have an amine. And amines, as we're going to explore in later chapters, are derivatives of ammonia. Whenever you have a carbon chain as your R group and it is connected to a nitrogen, it could be NH2, it could be NH in an additional carbon chain. That is known as an amine. Lastly, if you have a carbon chain connected to an SH group, that is known as a thiol group. The last family of compounds or functional groups is called a carbonyl group. A carbonyl group, it is identified because of the presence of the carbonyl functionality. So this carbonyl functionality is the carbon double bonded to oxygen that each one of these functional groups have. The different functional groups that have a carbonyl group include an aldehyde. And in order for something to be called an aldehyde, to either side of that C double bond O, you need to have at least one hydrogen. The other group, the R group, the rest of the molecule could be a hydrogen or a carbon chain. The next functional group is called the ketone. In a ketone, you have a carbonyl group that on either side of the carbonyl group, you have carbon chains. Both R groups need to be carbon chains. The next functional group is called carboxylic acid. And in a carboxylic acid, we have a carbonyl group connected to one side of the molecule. Doesn't matter if it's on left or right, an OH group. This R group could be a hydrogen or it could be a carbon chain. Next is an ester. In an ester, you have a carbonyl group that is bonded with a single bond to oxygen, and that single bond to oxygen must be connected to a carbon chain. So the R group that I'm highlighting with that red dot must be a carbon chain. The R group that is next to the carbonyl on the other side, that does not include that single bond to oxygen, can be a hydrogen or it could be a carbon chain. Lastly, the last member of the carbonyl group functionality group is called an amide. When it comes to an amide, we're going to have a carbonyl group connected to nitrogen. It doesn't necessarily need to be NH2. It could be an H with additional carbon chains, but as long as you have a carbonyl group connected to nitrogen, that constitutes as an amide. The R group that you see on the other side of the carbonyl could be a hydrogen or could be a carbon chain. So now, how do we apply all this knowledge in order to basically explore organic compounds? Well, functional groups are going to be present in many molecules that are known as organic compounds. And we can see illustrated here two different organic compounds. On the left side of the slide, we actually have a form of vitamin B6. And on the right side of the slide, we have jasmonate. So the left molecule, vitamin B6, is an important vitamin in the body, while the molecule on the right, jasmonate, it is actually responsible for the smell of jasmine. In order to clearly illustrate what are the functional groups in these compounds, I'm going to utilize as an example jasmonate. So when we look overall at the structure of jasmonate, we can observe that there's several functional groups present. We can observe also that part of this molecule shows you skeletal, part of the molecule shows you condense. Now, we are just starting organic chemistry, so to benefit most students, I'm going to write in all the carbons and hydrogens that are present in the molecule. So at least you can see where these functional groups that I'm selecting and identifying are present in the molecule of jasmonate. So overall, the molecule has carbon here, 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 and here. So that's the illustration of the carbon atoms that are present. Using my highlighter tool, I'm going to identify the functional groups that can be found in this molecule. The first functional group that I can identify is a carbon-carbon bond that is connected by a double bond. That functional group is known as an alkene. As I move throughout the molecule, the next functional group that I identify is going to be a carbon chain connected to a carbonyl, and that carbonyl is connected to an additional carbon chain. So that functional group, as you can see here, that is known as a ketone. As I walk throughout the molecule, the next functional group that I observe is when I have a C, double bond to O, single bond to oxygen. That oxygen is connected to a carbon chain. And I can see that I have another area here. But simply by having C, double bond O, single bonded to oxygen, and that oxygen is connected to a CH3, that is known as an ester. For practice, I'm going to highlight the functional groups that are present specifically in vitamin B6, and I want you to be able to identify them. Let's get started. The first functional group that I see here, let me first add the carbons and hydrogens. So there's a carbon right here connected to a hydrogen, carbon right here, here, here. This one right here, here, here. Right there. So those are the carbon atoms in the molecule. First, what is the functional group present when a carbonyl, to one side it has a hydrogen, and to the other side it has a carbon chain? Next, what is the functional group when I have a carbon chain connected to an OH group? Lastly, what is the functional group when I have a carbon chain connected to nitrogen? And these are the functional groups that are present in vitamin B6.